Picture the Earth not as a stable sphere turning beneath a steady sky, but as a planet whose invisible shield is drifting, bending, and slowly losing its grip. For most of human history, the magnetic poles wandered only slightly, shifting, in ways that hardly mattered to anyone alive. But in the last century, something changed. The North Magnetic Pole broke into a sprint, racing across the top of our planet faster than at any recorded time in geological memory. And underneath that motion, the strength of the magnetic field itself has been slipping. Not evenly, not quietly, but in distinct patches and fractures that hint at deeper instability. In some regions, especially over the South Atlantic, the field has thinned by nearly a third. It is as if the Earth's shield one that has protected us from cosmic radiation for millions of years has developed a soft spot. So what does that actually mean? For us, for the satellites circling above us, for the aircraft threading the polar skies, for the power grids humming across continents. The magnetic field is not decoration. It is a deflector, a cushion, a quiet guardian against particles that would strip our atmosphere and wash the surface in radiation. The moment it weakens, even slightly, that protection falters. But here is where the story deepens. The rocks beneath our feet store a kind of memory. Inside ancient lava flows in crystals that froze in place hundreds of thousands of years ago lies a record of past magnetic fields, and that record is clear. The poles have not just wandered before, they have reversed entirely. North became south, and south became north, in events that played out over centuries or less. During those transitions, the field did not simply flip like a switch. It weakened, fragmented, and in some periods nearly collapsed before reassembling itself in a new orientation. In other words, the drifting we see today is not happening in isolation. It fits a pattern the planet has followed many times. And if the early stages of a reversal have begun, then the thinning of the field and the strange acceleration of the pole may be the first hints of a much larger rearrangement. For now, life on the surface feels unchanged. The sky looks the same. The compasses still point roughly north, but the instruments tell another story. Satellites passing through the weakened regions record brief surges of radiation. Navigational systems require more frequent recalibration. High-altitude flights face slowly increasing exposure to solar particles, and deep within the core, the molten metal flow that generates our magnetic shield appears to be shifting in complex, uneven ways. So the question grows, is this drift simply another chapter in the field's natural variation, or the opening move in a planetary transition we rarely witness? Scientists do not agree on the answer. Some say this is just an oscillation. Others argue that the speed of the drift, combined with the steep weakening, mirrors the early stages of known reversals. What is certain is that the field is changing faster than expected, faster than models predicted, faster than the slow, ancient rhythm we once believed governed the invisible architecture around our world. And it is this quiet acceleration that creates the tension beneath the calm. Because if the reversal has begun, whether it will unfold over centuries or decades, then everything we rely on in the modern age will feel the effects long before the poles actually switch. For a planet that has lived under the same magnetic orientation for almost 800,000 years, change does not announce itself with a roar. It begins with a drift, a subtle weakening, a shift so gentle and so slow that most of us never notice it at all. But the Earth notices, and the sky feels different when the shield beneath it starts to move. In the next part, we will step into the geological record itself, into the ancient stones that witnessed previous reversals, and see what those forgotten transitions can tell us about the future, unfolding quietly above our heads. If you want to understand what comes next, you have to begin with the only witnesses that have already seen it happen. Not people, not stories, but stones, quiet layers of ancient volcanic rock that hold a frozen snapshot of the Earth's magnetic field at the moment they cooled. They are not mysterious, they are not symbolic, they are physical memory preserved grain by grain. When geologists first began to study these records, they expected subtle variations, gentle drifts, maybe a few unexpected bends in the field. What they found instead was far more dramatic. Complete magnetic reversals written into the minerals like pages in an old diary, north becoming south, south becoming north, the field collapsing into a tangled, weakened maze before reassembling itself with the poles flipped. Each reversal is not a single moment. It is a process that unfolds over centuries or sometimes less, and the stones show this pattern with unsettling clarity. As lava cools, iron-bearing crystals align themselves to whatever the magnetic direction happens to be at that exact instant. Layer by layer, eruption after eruption, the orientation changes, sometimes dramatically within a relatively small vertical span. The result is a geological film strip of a world in transition. Put simply, the Earth has done this many times before, and it will do it again. But what matters most is not that the poles have reversed, it is how the planet behaved on the way there. During these transitions, the magnetic field weakens significantly. In some intervals, it becomes so disordered that there is no meaningful north or south at all, only drifting pockets of magnetic intensity scattered across the globe, a fragmented shield, a world without a clear direction. And when the shield weakens, the consequences extend far beyond compasses. The atmosphere becomes more exposed to charged particles from the sun. Radiation belts shift unpredictably. The auroras drift toward the equator. In the ancient world, none of this disrupted technology because technology did not exist. But today, that same weakening would touch nearly every system we depend on. The geological record also reveals something else, something that feels strangely familiar. The early stages of a reversal often begin with regional thinning of the magnetic field, especially in mid-latitude zones. Not everywhere at once, not catastrophically, but in isolated patches where the field grows soft. These patches widen, deepen, and eventually merge into a global decline. And if that pattern sounds familiar, it is because one such thinning is already happening. But we will return to that soon. For now, picture a long-dead lava flow somewhere in the ancient world. A wall of once molten stone stands in silence, its crystals aligned not with the magnetic north you know, but with a direction long forgotten. Another layer above it points elsewhere entirely, and another, and another. A slow, disorienting twist captured in a language only rocks can speak. In other words, the Earth has been here before. It has drifted, faltered, and rebuilt its magnetic identity many times. The reversals are not rare. They are part of the planet's rhythm, a rhythm too slow for civilizations to remember, but perfectly preserved in the stones beneath our feet. What the rocks cannot tell us, however, is how quickly the next transition will unfold. Some past reversals stretched across millennia, others happened in a fraction of that time. There is no guarantee that the process will be gentle, nor is there certainty that we have centuries to prepare. The geological memory offers a warning, but not a timeline. And this brings us back to the present, to a place on the map where the field is already thinning in ways that match the earlier stages of those ancient transitions. A region where satellites flicker, instruments falter, and the shield dips lower than anywhere else on Earth. In the next part, we will look directly at that place, the South Atlantic anomaly, a growing zone of weakness that may be the first visible crack in the Earth's magnetic armour. There is a place on Earth where the shield grows thin, a region so unusual that satellites passing overhead often shut down their sensitive instruments or switch into safe mode just to survive the transit. It stretches over the South Atlantic and parts of Brazil, an invisible depression in the magnetic field known simply as the South Atlantic anomaly. To the naked eye, nothing looks different there. The sky is the same blue, the ocean reflects the same sunlight, and life proceeds as it always has. But hundreds of kilometers above, the situation changes abruptly. Satellites move through a pocket where the protective strength of the magnetic field dips to some of the lowest levels found anywhere on the planet. In this weakened zone, energetic particles from space plunge deeper than they should, striking hardware that was never meant to endure such exposure. Telemetry logs tell the story. Instruments glitch without warning, sensors develop brief blind spots, memory units flip bits from 0 to 1 and back again. In severe cases, an entire satellite may shut down until it clears the region. Engineers have learned to expect these failures. They adjust flight software, alter observational windows, and build contingencies around a region that behaves like a bruise on the Earth's magnetic skin. In other words, the shield is not even. It has weaknesses. And this one is growing. The anomaly has expanded in size over the past decades, slowly widening like a dent spreading across the surface of a drum. Its intensity is deepening as well, with measurements showing a steady decline in field strength. This is not just a technical inconvenience. It is a sign that the internal engine generating our magnetic protection, the churning liquid iron of the outer core, is behaving differently beneath this part of the world. Why here? Why now? The answers are complicated, but the consequences are straightforward. As the field weakens, more radiation reaches lower altitudes. High-altitude flights over the region receive slightly increased exposure. Satellites that rely heavily on precision timing must compensate for unexpected errors. Even the International Space Station experiences heightened particle impacts when it passes through the anomaly's upper edge. So what does this mean for us? For now, the effects are mostly technical, but the pattern is familiar to anyone who has studied past magnetic reversals. In ancient transitions, the decline of the field did not happen uniformly. It began with regional anomalies, localized pockets where the shield faltered, before the fragmentation spread globally. The South Atlantic anomaly is not proof of an impending reversal, but it is not inconsistent with one either, and perhaps that is what makes it so unsettling. The anomaly is not a hypothetical future or a theoretical model. It is a present reality, measurable, mapped, and expanding. It is the kind of early symptom the geological record warns us to take seriously, even if it does not tell us exactly where the process will lead. In other words, the Earth's magnetic armour has already found its first soft spot, and the shield does not fail all at once. It fractures, thins, and opens in places where we least expect it. If the weakening continues, the next effects may not be confined to orbiting machines. They may begin to touch systems much closer to the ground power infrastructure, communications, and the quiet assumption that the sky above us is always safe. In the next part, we will examine what happens when the field weakens further, how radiation behaves, how technology responds, and what the early stages of a world with a diminished shield might feel like from the surface of our own planet. When the magnetic field weakens, the change does not begin as a dramatic event on the ground. Life continues, the air feels the same, the sky looks unchanged, but above that quiet surface, the invisible boundaries that protect our planet begin to loosen. And as they do, particles from the sun travel deeper into the atmosphere than they ever should. We see the first signs of this not in cities or oceans, but in the realms where our machines touch the edge of space. High above the Earth, satellites move through shifting tides of radiation. Their electronics, built to withstand harsh conditions, start to record anomalies that engineers once considered rare. Not catastrophic, not constant, but unmistakable. A single charged particle passing through a memory unit can flip a bit, turning a 0 into a 1. A brief pulse can scramble a sensor reading. In most cases, the satellite corrects itself, but sometimes the correction fails. Instruments reboot, cameras shut off, software resets mid-operation, creating blind intervals in missions that depend on precision. For aircraft flying along polar routes, the effects feel different. At high altitudes, where the atmosphere is thin, the magnetic field normally funnels the most energetic particles toward the poles and keeps them far above the flight path. But when the field weakens, even slightly, those particles descend lower. Radiation monitors on certain flights have recorded brief spikes. Nothing dangerous to passengers, but noticeable enough that navigation systems occasionally switch to backup modes to avoid interference. In other words, as the shield softens, the space around us becomes noisier, more chaotic, more intrusive. This is not science fiction. It is a quiet shift already observed in data logs and flight records, and it mirrors what we know from geological history. During past magnetic reversals, the field did not simply fade evenly across the globe. It fragmented. It developed regions where protection dropped sharply, allowing radiation to seep into areas that had long been sheltered. The atmosphere absorbed the impact, but the surface environment changed subtly, especially in latitude bands unaccustomed to such exposure. For our modern world, which depends on precision electronics, synchronized timing and global connectivity, even subtle changes carry consequences. Consider power grids. Transformers are sensitive to geomagnetic currents induced by space weather. When the magnetic field weakens, those currents become easier to trigger. Surges that once required massive solar storms may begin occurring during more moderate events, and this is where the picture deepens. A weaker shield does not just let in more radiation, it lowers the threshold for disruption. Events that were once considered extreme outliers begin to move closer to the realm of possibility. The kinds of solar storms that our ancestors witnessed as awe-inspiring lights in the sky now have the potential to interfere with satellite networks, GPS timing, or the stability of large power systems. So what would a world with a much weaker magnetic field feel like from the ground, from everyday life? It would not look apocalyptic. There would be no moment when the sky suddenly turned alien. Instead, the changes would accumulate slowly. More frequent auroras at unusual latitudes, occasional communication blackouts during solar activity, subtle increases in high-altitude radiation, and a rising risk to the infrastructure we rely on every day. Nothing dramatic at first, but unmistakable in the long view. And this leads to the central question one that divides researchers studying the past and the present alike. If we are already seeing the early signs of weakening, if anomalies like the South Atlantic region are expanding, and if the poles continue their rapid drift, then why can't scientists agree on whether the reversal has truly begun? In the next part, we'll step into that debate, into the evidence, the uncertainty, and the conflicting interpretations that shape the question of whether we're living through the early stages of a planetary transition. When scientists look at the magnetic field today, they all see the same basic picture. The poles are drifting, the strength of the field is declining, and regional anomalies are growing. The data itself is not controversial. What is controversial is what the data means. Some researchers argue that the current changes fall well within the natural variability of the magnetic field. They point out that the field has always fluctuated, sometimes dramatically, without necessarily heading toward a reversal. In their view, the accelerated drift of the North Magnetic Pole and the deepening of the South Atlantic anomaly are unusual, yes, but not unprecedented. These patterns, they say, could stabilize again, just as they have in earlier chapters of the field's long and restless history. Others disagree, strongly. To them, the combination of rapid pole movement, regional weakening, and measurable changes in the flow of the Earth's core suggests something more significant. They note that the last full reversal happened almost 780,000 years ago, which is long by geological standards. Several studies indicate that we may be overdue, not in a precise sense, but in the way one might say a forest overdue for a lightning strike, not guaranteed, but statistically primed. The tension between these viewpoints does not come from ignorance. It comes from the limits of what we can know. The magnetic field is generated deep within the Earth's outer core, an ocean of liquid metal we cannot directly observe. Every model we build relies on measurements taken at the surface or from satellites, filtered through assumptions about what happens thousands of kilometers below. And those assumptions matter. Small changes in a model can produce drastically different long-term predictions. Some simulations show the field stabilizing for centuries, others show the beginning of a collapse. In other words, the science is not uncertain because the experts are confused. It is uncertain because the planet itself is more complicated than any model we can construct. There is also the question of time. Even if a reversal is beginning, the process does not unfold on human schedules. A transition might take thousands of years, or it might accelerate rapidly, as some past reversals appear to have done. The geological record shows both possibilities, slow declines, and surprisingly fast flips. And so the debate continues, shaped by data that is compelling yet incomplete. But beneath that debate lies a quieter concern, rarely stated outright. A weakening magnetic field affects our modern world long before a full reversal occurs. That part of the discussion is not theoretical. Declining field strength means increased vulnerability to solar storms. It means more frequent satellite anomalies, more geomagnetic currents in power grids, and more radiation reaching altitudes where modern aviation travels every day. These effects do not wait for the poles to switch. They emerge as soon as the shield begins to soften. So the real question may not be, are we heading into a reversal? It may be, how much weakening can our technology tolerate before the consequences become unavoidable? And that brings us to one of the most intriguing pieces of evidence, an observation that does not settle the debate, but reframes it. Something happening not deep below us, but high above, where the edge of the magnetic field meets the solar wind. In the next part, we'll look at that observation and why some scientists believe it could hold the first clear hint of where this transition is truly headed. Far above the Earth, where the atmosphere thins into darkness, the magnetic field stretches outward like a vast invisible bubble. This bubble, our magnetosphere, shapes itself around the solar wind, forming a boundary where charged particles are diverted and slowed. It is here, at this fragile frontier, that scientists have noticed something unusual. Under normal conditions, the magnetosphere compresses and relaxes depending on the strength of the solar wind. Its shape shifts, but the structure holds. The radiation belts rise and fall slightly, following predictable patterns. But in recent years, instruments on multiple satellites have detected disturbances that do not fit these patterns, brief surges of high-energy particles slipping deeper into the magnetosphere than expected, even during moderate solar activity. These events do not last long. They are measured in minutes, but they are out of place. The kind of particle penetration normally associated with strong geomagnetic storms has begun appearing during weaker ones, as if the shield's threshold has quietly lowered. In simple terms, the barrier between Earth and space is behaving as though it is thinner. One example came during a series of mild solar wind streams. Nothing extraordinary by historical standards, yet several satellites recorded particle intrusions intense enough to trigger automated protective modes. The solar wind speed was not remarkable, the density was typical. But the magnetosphere's response was not. The protective bubble contracted more sharply than models predicted, allowing radiation to dip into orbits that are usually safe. This is not definitive proof of a weakening field, but it is consistent with one, and that consistency is what concerns researchers. If the shield is softening globally even slightly, then the effects will appear first at the edges, where the magnetosphere absorbs the constant pressure of the solar wind. From there, the changes migrate inward, toward the regions where satellites orbit and where the upper atmosphere meets the flow of particles streaming from the sun. The radiation belts offer another clue. These torus-shaped zones of trapped particles shift in position as the magnetic field changes. Recently, they've shown patterns of compression and drift that are difficult to explain using the old assumptions. Not dramatic changes, not enough to declare a new era, but enough to suggest that the magnetic scaffolding holding them in place is no longer as stable as it once was. If this interpretation is correct, then the earliest signs of a larger transition are already visible, not on the ground, not in the behaviour of compasses, but at the very edge of the field where the shield meets the solar wind. And this raises a deeper question. If the magnetosphere is responding first, and satellites are responding second, then where exactly in that sequence do we stand? Because during past transitions, the surface felt the effects last. By the time ancient environments began to change, the deeper layers of the magnetic field had already shifted for centuries. If that pattern holds, then what we are seeing now may not be the beginning of a transition, but the middle of one. In the next part, we will explore how these changes could cascade downward, how subtle shifts at the outer boundary eventually touch weather, radiation levels, biological systems, and the quiet assumptions that life on the surface takes for granted. From the ground, the first hints of change arrive in ways that are easy to mistake for coincidence. A strange light in the sky at a latitude where no one expects it. A brief loss of radio contact during a flight that never used to experience such interruptions. An unusual reading on a radiation monitor at an observatory, noted, logged, and then filed away. Nothing dramatic, nothing that announces itself as the beginning of anything. One of the earliest visible signs of a weakening magnetic field would be the behaviour of the auroras. Those curtains of green and red light that usually dance near the polar circles might begin appearing farther from their traditional homes. People in regions unaccustomed to such displays could occasionally look up to find the sky softly glowing, the upper atmosphere energized by particles that have wandered into new territory. For most, it would feel like a beautiful anomaly, a rare gift, a story to tell. But behind that beauty lies a quiet shift in the way our planet interacts with the stream of particles flowing from the sun. As the field weakens and its boundaries fluctuate, the zones where atmospheric atoms are excited move with them. The lights in the sky become a kind of living map of where the shield is thin. At the same time, the invisible environment around us changes in ways only instruments can see. Background radiation levels at high altitude inch upward. The dose received during a long-haul flight creeps a little higher, still within safe limits, but no longer quite the same as it was a century ago. Sensitive experiments on the ground, those studying cosmic rays or particle interactions, have to account for a slowly shifting baseline. In other words, the world does not suddenly become dangerous. It becomes subtly different. For many forms of life, that difference is absorbed without fanfare. The Earth has endured stronger radiation before. The biosphere has persisted through countless reversals. But for a civilization that relies on finely tuned technology, the margins are narrower. Small increases in radiation can shorten the lifespan of satellites, corrupt data, or damage delicate sensors used for climate monitoring, navigation, and communications. Even weather forecasting, which depends heavily on fleets of orbiting instruments, may begin to feel the strain, not through obvious failure, but through a slow erosion of reliability as certain orbits become more hostile to electronics. As some satellites fail earlier than expected, gaps in coverage open unless new ones are launched in time. On the surface, people may notice occasional disruptions that are hard to explain. A navigation system behaving strangely during a geomagnetic disturbance, a temporary drop in radio reception, power grid operators receiving alerts about induced currents during solar events that once passed unnoticed. Individually, each of these moments seems minor. Together they form a pattern, a world where the sky above is no longer as quiet as it used to be. So what does that feel like day to day? It feels like living in a house where the walls are still standing, but the wind has found new ways to slip through the cracks. You do not see the structure fail. You hear a new whistle in the corners. You feel a draft where there was none before. Life goes on. But the sense of solidity begins to fade, even if you cannot quite say why. For now, we stand at the beginning of that feeling. The majority of people on Earth have never heard of the South Atlantic anomaly, never looked at maps of shifting poles, never seen the data from satellites at the edge of the magnetosphere. And yet we all live under the same sky, held together by the same shield that is changing a little more each year. The Earth has survived every reversal it has ever experienced. Life has adapted, persisted, and evolved through them all. The question is not whether the planet can endure another transition. The question is whether our particular way of living can. Because our civilization is built on assumptions the rocks never had to make. That satellites will always stay up, that electricity will always flow steadily, that the thin, invisible barrier protecting our atmosphere will behave tomorrow the way it behaved yesterday. In the next part, we'll step back and look at those assumptions directly, at the fragile architecture of our technological world, and what it means to depend so completely on a shield we did not build and do not control. Modern civilization is built on foundations that appear solid but are in many ways astonishingly delicate. Power grids, communication networks, navigation systems, climate monitoring, banking, aviation. Each of these depends on technologies that assume a stable magnetic environment. And for most of our history, that assumption held true. But as the magnetic field weakens, that stability becomes less certain. Electricity, for example, seems firmly grounded in the infrastructure around us. Steel towers, copper lines, substations humming quietly behind fences. Yet much of this system is vulnerable to disturbances caused by geomagnetic currents. When the magnetic field fluctuates, it induces currents in long, conductive lines. In extreme cases, those currents can damage transformers or cause regional blackouts. Events like these have happened before, even with a stronger shield. Communications rely on satellites orbiting above the atmosphere, machines that operate in the zone where magnetic protection matters most. Many of these satellites depend on precise timing signals, fractions of microseconds that coordinate financial transactions, synchronization of networks, and global positioning. A single glitch in timing can ripple through entire systems, disrupting services far beyond the point of failure. Navigation, too, depends on reliability. GPS satellites broadcast signals that tell planes where they are, guide ships through narrow channels, and allow emergency responders to move with confidence. But as the environment above Earth grows more unpredictable, satellite lifespans shorten. The orbits we rely on become less stable, and each failure creates cascading effects on the ground. Even the simple act of knowing the time becomes more complex. Many satellites serve as reference clocks for countless technologies. If radiation forces them offline or distorts their data, the infrastructure that keeps our digital world synchronized falters. It is not dramatic no explosions, no cinematic flashes of light, but it is deeply disruptive, and this is the quiet truth. The strength of our civilization lies not in its physical structures but in the invisible threads connecting them. Threads woven from timing signals, data packets, electrical currents and orbital mechanics. Threads that depend, in ways we rarely consider, on the behavior of a magnetic field generated deep within the Earth. A weaker shield does not destroy these systems outright. It strains them. It narrows the margin for error. It moves the threshold where ordinary space weather becomes a genuine hazard. In a world with a declining magnetic field, events that once passed unnoticed could begin to leave marks, small ones at first, like static on a radio signal or a temporary loss of precision in navigation. But as the weakening progresses, those marks deepen into patterns, and the patterns begin to shape outcomes. None of this means that civilization is on the brink of collapse. The Earth has faced far greater cosmic challenges, and humanity is adaptable. But adaptation requires awareness, preparation, a willingness to see the invisible structure of our world for what it truly is, a complex architecture balanced on the assumption of a stable shield. And this brings us back to the scientific debate. If the weakening continues, do we have decades, centuries, longer? The uncertainty shapes how governments plan, how engineers design, and how researchers interpret the trends unfolding above us. In the next part, we'll explore why this uncertainty persists and what the Earth's core itself may be telling us about the direction and pace of the magnetic field's evolution. Deep beneath the continents and oceans, far below the crust and mantle, lies the engine that shapes our magnetic world. It is a sphere of molten iron and nickel, swirling in currents as vast as continents, heated from within, and moving in patterns we can only infer. This is the Earth's outer core. A metal ocean thousands of kilometers deep, generating the magnetic field through motion alone. We cannot see it. We cannot sample it. Everything we know comes from indirect clues. Seismic waves trembling through the planet, changes in the magnetic field measured at the surface, and models that attempt to recreate the behavior of a system hidden from view. And yet, for all this uncertainty, one thing is clear. The flow of the core is not constant. It shifts. It accelerates. It reorganizes itself over decades and centuries, creating ripples that move upward through the mantle and ultimately shape the magnetic field we rely on. In recent decades, those ripples have changed. Measurements show that certain regions of the core's flow have sped up, while others have slowed. Some appear to be drifting eastward, others deepen or rise like slow, powerful currents. The result is a magnetic field that no longer behaves as it once did, a field whose poles wander unpredictably and whose strength declines unevenly across the globe. In simple terms, the core is moving differently than before, and the magnetic field is responding. To understand the scale of this movement, imagine a river the size of a hemisphere, flowing in loops that span thousands of kilometers. Now imagine that river changing its speed, splitting into new branches, or shifting its course entirely. The magnetic field is the map of those changes, a signal written in lines of force rather than ink. When researchers simulate the core's flow, they often find that the patterns associated with pole reversals share familiar signatures: regional weakening of the field, rapid pole drift, and irregularities in the flow beneath regions like the South Atlantic. These simulations are not perfect, but they show how sensitive the magnetic field is to subtle changes deep below. The challenge is that we cannot match the simulations to the real world with perfect accuracy. We know the direction of the field, we know its strength at different points on the surface, but the details of the core's internal flow remain, in many ways, hidden. This uncertainty is the root of the scientific disagreement. The data tells us the field is changing, but it does not tell us how quickly the core will continue to evolve. And then there is the question of timing. Some reversals in the geological record took thousands of years to unfold. Others seem to have happened far more quickly within centuries, or even less in localized regions. The pace of a reversal depends not only on the strength of the field, but on the specific flow patterns inside the core. Right now, those patterns are shifting. And the field is responding with a speed that has caught many researchers off guard. For example, the rapid drift of the North Magnetic Pole toward Siberia accelerated sharply during the 20th century. At the same time, the weakening of the field in the South Atlantic region deepened. These two trends, pole acceleration and regional weakening, suggest changes in the core that are more dynamic than previously believed. None of this proves that a reversal is underway, but it does raise a possibility that is difficult to ignore, that the engine driving the field is entering a new phase, one that could reshape the magnetic environment around our planet for centuries to come. And if this is true, then our understanding of time, of how long we have to adapt, may be far less certain than we assume. In the next part, we will bring these threads together and explore how the geological record, the behavior of the core, and the growing anomalies on the surface combine into a picture that is incomplete, yet impossible to dismiss. When you step back from the individual pieces, the drifting poles, the thinning shield, the disturbances at the edge of the magnetosphere, the shifting currents within the core, a larger picture begins to take shape. None of these changes alone tells the full story. But together, they suggest a magnetic system that is no longer behaving as it has for most of recorded history. The drift of the North Magnetic Pole is not just fast, it is accelerating. The South Atlantic anomaly is not just a weak spot, it is expanding. The magnetic field is not just fluctuating, its average strength is declining at a pace that has surprised researchers. And deep below, the core is not just moving, it is reorganizing itself. These observations do not prove that a reversal is underway. The Earth has experienced fluctuations before, periods when the field weakened and then recovered. But the combination of rapid drift, regional weakening, and altered core flow forms a pattern that is difficult to dismiss. The geological record provides a kind of mirror to this moment. In past reversals, the early stages often included exactly these features: increased pole motion, irregular field intensity, and regional anomalies that grew in size before merging into a global shift. These were not dramatic signs to ancient eyes, but they were unmistakable in the minerals that recorded them. In other words, the planet often whispers before it shouts, and today those whispers are growing louder. Scientists are careful with their conclusions because the system is incredibly complex. A few decades of data cannot fully capture the behavior of a mechanism that evolves over millennia. But caution does not erase the fact that something is changing, and changing in ways that align with what we know from past transitions. This does not mean the field will collapse tomorrow, or even within our lifetimes. A reversal could still be centuries away, or it could accelerate as some have done before. What matters is that the signs we are seeing today resemble the early stages of events that reshape the magnetic environment of Earth in profound ways. And this raises a different kind of question, one that extends beyond physics and into the realm of civilization and time. If the magnetic field is entering a transition, then the changes we experience now are the earliest steps in a process that could span generations. The effects will accumulate slowly, shaping technologies, infrastructures, and the assumptions that future societies make about the stability of the sky above them. A transition of this scale is not a human-scale event, it is a planetary one. And standing at the beginning of such a transition, if this is indeed what we are witnessing, means living in a moment where the familiar is shifting, but not yet transformed. A moment where the world feels unchanged on the surface, even as deep forces begin to alter the foundation beneath it. In the next part, we will explore what this means for the future, not in apocalyptic terms, but in practical, generational ones. How societies adapt, how technology evolves, and how life continues under a sky that may slowly, quietly, become different from the one our ancestors knew. If the magnetic field is moving toward a transition, it will not announce itself with a single moment. There will be no day when the sky suddenly changes, no instant when compasses spin wildly across the world. Instead, the process unfolds across centuries. It is slow by human standards, but swift in geological time and in-between state, where the planet is adjusting, reorganizing and reshaping its magnetic identity. For people living through such a transition, life continues almost normally. Generations rise and fall during periods when the magnetic field is weakening or drifting, and most never realize the changes underway. The ground remains steady. The seasons follow their familiar rhythm. The sun rises in the east, even if the magnetic north moves somewhere else entirely. But subtle differences emerge. Auroras appear farther from the poles, becoming a familiar sight in places where they were once unheard of. Airlines adjust their routes more frequently during solar storms. Power grid operators learn to anticipate geomagnetic disturbances as part of regular planning, not rare events. Technology evolves as well. Satellites are redesigned with greater shielding. Orbits are chosen to minimize time spent in regions of high radiation. Communications networks become more resilient, built with the expectation that interruptions may happen more often. In a sense, society adapts, not dramatically, but steadily, to a sky that becomes slightly more active with each passing decade. And while these changes may seem small individually, they accumulate. They shape the world into something subtly different from the one we inherited. A long transition also means that different generations experience different realities. Children grow up thinking it is normal to see the northern lights from latitudes where older adults never saw them. Engineers entering the workforce assume that frequent satellite resets or radio disturbances are simply part of the job. Pilots learn new procedures for navigating during geomagnetic events. The baseline shifts quietly, almost imperceptibly, until the new conditions feel ordinary. This is how planetary change works when it unfolds on timescales longer than a human life. It does not overwhelm, it surrounds. The geological record shows that reversals have happened many times before, and life continued through all of them. The transitions were not sudden catastrophes, but long chapters in the Earth's ongoing story. And if another transition is beginning now, we are standing at the very start of a process our descendants may still be experiencing centuries from today. Yet there is one part of the transition that belongs uniquely to us: our dependence on technology. No past civilization relied on satellites, power grids, or global communication. No earlier era had infrastructure that could be disrupted by the sky itself. And that makes our relationship to the magnetic field fundamentally different from that of any species before us. Whether the field ultimately reverses or simply fluctuates, the coming decades will require awareness and adaptation. Not fear, but understanding. Not panic, but preparation. The sun will continue to rise. Life will go on. But the world we pass to future generations may reflect a sky that behaves differently from the one our ancestors knew. In the next part, we will explore this generational perspective more deeply, how human history intersects with planetary cycles, and how civilizations adapt when the forces shaping their world move on timescales far beyond their own. Human history is a thin layer on the surface of a very old world. Our calendars, our stories, our recorded events stretch back a few thousand years long, enough to feel deep to us, but almost weightless compared to the timescales on which the Earth itself changes. Continents have drifted, mountains have risen and worn away, oceans have opened and closed. Through all of this, the magnetic field has flipped, weakened, recovered, and twisted countless times. Entire species have come and gone without ever knowing that the sky above them was quietly rearranging its invisible lines of force. By comparison, our presence here is brief. We arrived in the middle of a chapter already in progress. For as long as humans have looked at the night sky, the magnetic poles have been roughly where we expect them. Compasses point north, auroras hover near the polar circles. The field is strong enough that space weather remains mostly a distant curiosity. To us, this feels like the default state of the world, a baseline we assume has always existed. But in the larger context of planetary time, it is simply a phase, a stable moment between transitions. When we place our brief timeline against the record preserved in rocks, ice cores, and sediments, a different picture emerges. Civilizations rise and fall within narrow windows between glacial cycles, between major volcanic events, between magnetic reversals. We build our infrastructure, write our histories, and imagine permanence in the spaces between these slow, powerful shifts. In other words, we are guests in a house that has been remodeling itself for billions of years. That does not make our achievements less meaningful. It makes them more fragile. The magnetic field is one of the quiet background conditions that allowed our particular version of civilization to develop. It shaped the radiation environment at the surface, the stability of the atmosphere, and the way the planet interacts with the energy pouring in from the sun. We did not design this environment, we inherited it. And now there are signs that one of its key features is changing. This does not mean that the planet is turning hostile. Reversals and fluctuations are part of its normal behavior. But it does mean that the conditions under which our systems evolved are not guaranteed to remain the same. The way we navigate, communicate, and power our world is tuned to a magnetic field that may be slowly stepping away from its current configuration. When you look at it this way, the question shifts. It is no longer, will the poles flip in our lifetime, or is a reversal already underway? It becomes, what does it mean to live in a time when the background rules of the planet are in motion? That is not a question a single study can answer. It is a question for generations for scientists, engineers, and ordinary people who will live through different stages of whatever transition unfolds. The Earth will continue its cycles with or without our attention. Fields will strengthen and weaken. Poles will wander and eventually reverse. Our role is not to stop these changes. We cannot. Our role is to understand them well enough to live within them, to build systems that can endure under a shifting shield, and to remember that stability has always been, in some sense, an illusion we draw over a restless planet. In the next part, we will bring this perspective back to the present moment, to what we can do now, what it means to be aware, and how quiet knowledge of a moving magnetic field changes the way we look at the sky above us. Right now, the magnetic field above us is not the same one that existed a century ago. It is weaker, more irregular, and shaped by currents in the core that continue to evolve beneath our feet. Yet daily life goes on with no outward sign of this change. We drive to work, fly between continents, map our cities with satellites, and navigate oceans with signals beamed down from orbit. The sky feels steady. The world feels familiar, but the instruments tell a different story. Every year, global magnetic surveys are updated, and every year the maps shift a little more. Navigation charts used by pilots and sailors must be revised, not dramatically, but consistently. A runway aligned perfectly with magnetic north in 1980 now points subtly elsewhere. Compasses that once needed adjustment every few decades are now recalibrated far more often. These corrections are small enough that most people never notice them, but together they reveal the quiet evolution of the magnetic field, an evolution unfolding in real time. The changes are not dramatic, not alarming, not something that interrupts the rhythm of society, yet they are undeniable. They show a system in motion, one that no longer fits neatly within the expectations of the past. We are not living through a moment of crisis. We are living through a moment of transition. In laboratories and research centres around the world, scientists track these shifts with growing curiosity. Observatories monitor the field from the ground. Satellites map its structure from above. Computers simulate the flow of molten metal deep within the core. Each component provides a different piece of a puzzle that is still incomplete. But one idea comes up again and again. The pace of change is increasing. Magnetic north is not wandering randomly. It follows a path that appears to be driven by competing regions in the core, each influencing the field in different ways. These regions move, they strengthen, they weaken, and the pole responds. At the same time, the overall strength of the field continues its slow decline. Not a collapse, not a free fall, but a measurable reduction that aligns with the early phases of past transitions. The present moment is not defined by certainty, it is defined by motion. And to live in such a time is to understand that stability is not permanent. It is a phase, a temporary arrangement, a balance that shifts quietly, until one day the difference becomes impossible to ignore. In the next part, we will explore what this means for the technologies that define modern civilization, and how they may need to change if the field continues its long, quiet drift. For most people, the changes in the magnetic field will never feel dramatic. They will feel subtle, almost atmospheric shifts that are easier to sense after years of hindsight than in the moment itself. The sky will still look familiar. The oceans will rise and fall as they always have. The world on the surface will appear unchanged. But beneath that familiar surface, the slow transformation leaves traces. Children growing up during a period of magnetic weakening might see auroras at latitudes where their grandparents never did. What begins as a rare spectacle, an unexpected glow on the horizon, may, over time, become something that happens often enough to feel normal. Stories will shift. I remember when the lights came only in winter, someone might say. Now they're part of every season. For communities that rely on radio communication, minor disturbances may become more routine. Static during solar events, brief dropouts in transmission, small mismatches in timing, things once considered anomalies will gradually become expected. Most people will not know why. They will simply adapt, adjusting procedures, learning new habits, responding without ever realizing that the root cause lies in a shield they cannot see. In rural areas far from city lights, nighttime observers may notice variations in the clarity of the sky. On certain nights, high-altitude air glow, normally faint, may appear brighter, shifting subtly with changes in the upper atmosphere. Pilots, gliding through high altitudes, may learn to recognize fluctuations in instrument behavior that were rare only a century earlier. Farmers might see slight changes in how certain plants respond to increased cosmic radiation. Nothing drastic, nothing harmful, but enough to nudge growth cycles or influence how seeds germinate at higher latitudes. Animals that navigate using the magnetic field birds, whales, bees, may adjust their migration paths gradually, altering routes in ways that feel strange at first but soon become the new pattern. Life continues, but the sky above is slowly rewriting its quiet rules. For the average person, the most noticeable changes may come through technology. A moment of lost GPS accuracy during a long drive, a delay in satellite-based weather data. A flight path shifted unexpectedly due to increased radiation over the poles. Small things easily forgotten until they begin to form a pattern. And in that pattern, the story of the magnetic field quietly unfolds. The planet has lived through transitions before. Ancient humans witnessed shifts they could not name. Early civilizations may have seen unexpected auroras, or felt strange compass behavior without understanding its cause. If a reversal is unfolding now, we will not experience the full arc of it. Our lives are too brief, our generations too short, but we will experience the beginning. The first pages of a chapter that others will continue to read. This is the nature of living on a changing world. Most cycles run longer than any single human life. We inherit a world in one state and pass it on in another. What matters then is not fear of the unknown, but awareness. A recognition that the sky is not a static ceiling above us, but a living interface between Earth and the Sun, a dynamic region shaped by forces far older than our species. In the next part, we will look deeper into the idea of time how planetary cycles unfold across vast spans, and what it means for humanity to witness even the earliest hints of such a cycle in motion. Time moves differently on a planetary scale. The moments that shape the Earth's magnetic history are not measured in years or decades or even generations. They unfold across thousands of years, slow arcs of change that are invisible in the span of a single human life. Civilizations rise, build, collapse, and rebuild, while the magnetic field completes only a small fraction of its long-term cycles. To us, the field appears steady because our lifetimes are too short to perceive its full motion. A drift that feels rapid to scientists today might be only a whisper in the geological record. A weakening that alarms researchers could be a prelude to a recovery, or the early steps of a transition that will not finish until long after our era is forgotten. This mismatch between human time and planetary time shapes the way we understand the world. We assume that the conditions we inherit are permanent. We imagine stability because, from our perspective, it has always been there. But the Earth is not static. It breathes, shifts, rearranges itself slowly. And in this slow turning of time, our species occupies only a brief moment. Consider the last reversal, nearly 780,000 years ago. Entire human lineages lived and died without ever sensing the deeper forces unfolding beneath their feet. The magnetic field was weakening, drifting, reorganizing itself, but the days still rose and fell. The glaciers advanced and retreated. The ancient world continued on, unaware that the sky itself was preparing to flip. Today, if a transition is beginning, we stand in a similar position. We feel stability because the pace of change does not disrupt our routines. We trust the world because it has always felt familiar, but familiarity is not the same as permanence. In the geological archive, we see periods where the field remained stable for hundreds of thousands of years, and others where it shifted quickly, almost abruptly, in ways that defy easy explanation. The Earth does not keep a regular schedule. It does not operate with predictable rhythms. Its cycles emerge from the deep, turbulent flow of molten metal that generates the magnetic field, and that flow follows patterns no one fully understands. What we do know is that time in the core moves differently than time at the surface. Changes that take centuries to propagate upward feel instantaneous once they reach the magnetic field. Variations that begin as subtle currents in the deep interior may become global phenomena long after the initial trigger has passed. In this sense, to observe the changes in the magnetic field now is to witness not an event, but a process, one that began long before we were born and will continue long after we're gone. A process we can measure, analyze, and try to understand, but never truly control. This should not frighten us. If anything, it connects us more deeply to the planet we live on. It reminds us that we're part of a story far older and far larger than ourselves. To live in a time when the magnetic field is shifting is to be invited into a chapter of Earth's long narrative. Not a crisis, not a catastrophe, but a transition, one that offers insight into the nature of our planet and the delicate conditions that make life possible. And this leads to a final reflection. In a world shaped by forces that move across millennia, what does it mean to be aware, to notice the early signs, to understand their significance, and to carry that understanding forward? In the next part, we will explore that question, bringing together the science, the history, and the quiet awareness that comes from recognizing that the sky above us is not fixed, but slowly, steadily changing. Most changes in the magnetic field do not announce themselves with dramatic events. They appear first as small irregularities, moments that are easy to overlook, easy to dismiss, until they accumulate into something that demands attention. These are the quiet signs of a system in motion. One of the earliest comes from the sky itself. Long before any reversal becomes obvious, high-altitude observers begin to notice subtle shifts in the behaviour of the upper atmosphere. Airglow becomes brighter on certain nights, reacting to increased particle activity far above the clouds. Satellites record fluctuations that do not correspond to any known storm, as if the boundary between Earth and space is breathing a little differently. Animals feel these changes even sooner. Migrating birds, whales, sea turtles, and countless insects navigate using magnetic cues. When the field shifts, even slightly, their routes drift with it. Scientists have documented migrations that veer a few degrees off their usual path, small enough that the animals still reach their destination, but strange enough to raise questions. A migrating bird does not know the magnetic field is weakening. It only knows that the direction it has followed for centuries has shifted. Whales occasionally beach themselves during magnetic disturbances, not because they are confused, but because the magnetic landmarks they rely on temporarily distort. Bees alter their foraging patterns. Salmon navigate rivers a little differently. The changes are subtle, but they echo through ecosystems in ways researchers are only beginning to understand. For humans, the quiet signs appear not in instinct but in technology. A pilot flying a familiar route notices the northern lights appearing farther south than expected, glowing faintly beyond the edge of night. A radio operator hears more static during periods of increased solar activity. a hiker's compass drifts a degree or two out of alignment, a GPS signal briefly loses accuracy in a region where reception has always been stable. None of these moments disrupt life, but they hint at a world gradually realigning itself. Even scientists who study the field describe moments of quiet surprise. Instruments that once produced steady lines now display slow oscillations. Measurements taken a year apart require small corrections that accumulate into larger revisions over time. Maps of the magnetic field, once updated every few decades, now require adjustments far more frequently. The signs are subtle, but they point towards something deeper. The magnetic field is not a fixed structure, it is a living system. And like any living system, it shows early symptoms long before the full transition takes shape. Not symptoms of failure, but of movement, an internal reconfiguration that starts in the core and ripples outward until it becomes visible at the surface. For most people, these signs pass unnoticed, not because they are invisible, but because they blend into the fabric of everyday life. A compass is slightly off, a satellite behaves strangely. The sky glows in an unexpected place. Each event seems isolated, each one feels unimportant, but together they form a quiet message. The shield above us is evolving. As this evolution continues, future generations may look back at these signs the way we look at early tremors before a geological shift. Not warnings, but indicators, clues that the system was already in motion, reshaping itself slowly while life on the surface carried on. In the next part, we will explore what it means to live through such a shift, not as observers of data, but as participants in a long unfolding chapter of planetary history. To live through a magnetic transition is, in many ways, to live through something that rarely announces itself. Unlike earthquakes or storms, a shifting magnetic field does not shake the ground or darken the horizon. It does not roar or flash or arrive in a single defining moment. It moves quietly, inching forward across decades, absorbing entire generations into its slow momentum. For most people, life will feel unchanged. The familiar routines continue. The rhythms of work, family, travel and seasons remain the same. But beneath that familiarity, the edges of experience begin to drift. Children born today may grow up in a world where auroras appear far from the poles, where pilots talk casually about minor radiation spikes, and where small interruptions in GPS or radio become part of normal operations. For them, these changes will not feel like signs of something unusual. They will feel like the natural shape of the world conditions inherited without question. A generation later, students might learn in school that Earth's magnetic field is in a long-term decline. They will memorize diagrams showing the drifting poles and the expanding South Atlantic anomaly, understanding these concepts not as warnings, but as environmental facts. The weakening shield will be part of the background of their education, the same way we now learn about climate cycles or plate tectonics. In technology, adaptation will become routine. Engineers will design equipment with new expectations in mind, stronger shielding for satellites, smarter routing for power grids, new methods for correcting navigation errors. Not because the world is in crisis, but because the conditions have shifted and technology evolves with them. People will talk about these changes the way we talk about weather patterns or long-term climate trends. Not with fear, but with curiosity. Someone might recall the first time they saw an aurora from a city much farther south than expected. Others will remember hearing about a solar event that briefly disrupted flights or communications. These memories will become the stories that mark the slow progress of the transition, tiny milestones scattered across years. And in nature, the adjustments will be just as subtle. Birds will subtly adapt their migratory cues. Marine animals will adjust routes. Some species may shift their breeding seasons or alter their patterns of movement in ways that future researchers will trace back to magnetic changes occurring today. Life will not pause. It will flow with the transition, adapting in real time, For scientists, living through such a shift will be a mixture of excitement and uncertainty. Measurements will continue, models will evolve, and debates will persist as new data challenges old assumptions. The lack of a definitive timeline will force researchers to think in broader terms, years blending into decades, decades into centuries, while still offering insights valuable to the moment we live in now. And through it all, the world will feel both familiar and subtly altered. A sky that once responded predictably to the sun will become a little more dynamic. A magnetic pole that once moved slowly will continue its accelerated journey across the polar regions. Compasses will drift, maps will adjust, technologies will refine themselves in the face of new conditions. This is what it means to live through a shift that spans generations, to inhabit a world where the changes are too slow to disrupt daily life, but too steady to ignore. It is not a crisis, it is not an emergency. It is a transition, a long, quiet rebalancing of forces deep within the Earth. And like all transitions on a planetary scale, it asks a simple question. How do we find stability in a world that is always moving beneath us? In the next part, we will bring this journey to its final reflection, what it means to inherit changing sky, and how awareness alone can transform our relationship with the world above us. The sky we inherit is not the same sky our ancestors lived beneath. It looks identical blue at noon, dark and full of stars at night, but its invisible structure has shifted. The magnetic field that shapes the boundaries between Earth and space is no longer in the same state it occupied for most of recorded history. The shield is changing, slowly but unmistakably, and we just happen to be alive at a moment when those changes become visible for the first time in many centuries. It's a strange kind of inheritance, one we didn't ask for, and one we often forget exists. We inherit landscapes, languages, cultures, and stories. But we also inherit magnetic conditions, radiation environments, and the subtle architecture of the sky. These elements form the background of our world, influencing everything from the stability of satellites to the migration of animals and the way our technologies respond to the sun. For thousands of years, humanity lived under a comfortably strong magnetic field. It shielded us from cosmic radiation, guided our navigation, and helped shape the conditions that made complex civilization possible. We built our sense of normalcy on that foundation, trusting, without even knowing it, that the invisible shield above us would remain steady and strong. But in recent generations, the field has weakened, the poles have drifted faster, and regional anomalies have deepened. These changes are slow enough that no one feels them directly, yet steady enough to show up in every scientific measurement. As a result, we are the first people in many lifetimes who can say with confidence, the magnetic field is not the fixed, immovable backdrop it seemed to be. To inherit a sky like this is to stand at a crossroads of time. Behind us lies an era of relative stability. Centuries when the magnetic poles moved slowly and the shield changed only in subtle ways. Ahead of us lies a long, uncertain journey where the field may continue to weaken, drift, or reorganize itself in patterns that only future generations will fully understand. And this is where the perspective deepens. Our descendants will not remember the world the way we know it today. They will inherit a different sky, one shaped by the continuation of the trends unfolding right now. Imagine a future where auroras dance over cities far from the poles, becoming a common part of the night sky. Children will grow up thinking it is normal to see the heavens glow in colours their great-grandparents saw only in stories. Pilots will train with new procedures that once seemed exotic. Navigation systems will be designed to gracefully handle the drifting pole positions and fluctuating magnetic intensity. And yet, to them, none of this will feel strange. It will simply be the sky they inherit. Just as our ancestors never questioned why the magnetic field guided their compasses so reliably, future generations may never question a world where the field behaves differently. Normalcy is not a fixed category. It shifts with the conditions we live under. Across centuries, even small changes accumulate into a new environmental backdrop, a different baseline, a rewritten default setting for the planet. But there is something uniquely human about our role in this moment. We are aware of the change. We can measure it, model it, interpret it. We can understand that what seems stable is actually fluid, that what feels permanent is quietly evolving, and that we are witnessing the beginning of a transition that will outlast us. No past society had this privilege. No previous civilization had the tools to see a reversal, or even its early signs taking shape. The sky we inherit is not one of fear, but of awareness. It invites us to see the planet not as static, but as living and dynamic, reshaping itself slowly over ages. It encourages us to take the long view, to imagine our moment not as an endpoint, but as a turning page in a much larger volume. In the next part, we will look forward beyond our moment, beyond our generation, to the quiet future that will unfold as the magnetic field continues its slow and restless evolution. The future shaped by a changing magnetic field will not arrive as a dramatic moment. It will not be marked by a headline, a sudden shift, or a point in time when the world collectively realizes what is happening. Instead, it will emerge the way most planetary changes do, quietly, steadily, almost invisibly, until the new conditions feel as natural as the old ones once did. In this quiet future, humanity will adapt without ever framing it as adaptation. Engineers will design spacecraft with the expectation that radiation levels will fluctuate more than they once did. Power grids will incorporate safeguards that automatically respond to geomagnetic variations. Pilots will learn updated procedures that assume the sky can behave in ways older generations rarely experienced. Navigation will evolve, not because the old systems fail outright, but because the shifting magnetic field will require new forms of precision. Satellites may rely less on the field for orientation and more on constellations of reference points, triangulating their positions in a sky where magnetic cues no longer behave predictably. Children born in that future will learn about the magnetic field the same way we learn about continents drifting, not as a threat but as a dynamic part of the planet's identity. Teachers will explain how the poles once moved slowly and later accelerated, how the field weakened and restructured itself, how ancient rocks preserved the signatures of past transitions. It will be part of the scientific story of the Earth, a narrative of change rather than instability. As decades pass, certain phenomena will become more familiar. Auroras at mid-latitudes, temporary disruptions in radio signals during solar activity, occasional alerts from power grid managers preparing for geomagnetic currents. None of these will define the era, but collectively they will colour its character. Life will continue, cities will thrive, planes will cross oceans, satellites will orbit the planet designed with new resilience. The magnetic field may weaken further before it stabilizes, or it may drift into a new pattern that scientists have yet to predict. What matters is not the fear of reversal, but the understanding that Earth's magnetic field has changed many times before and will change many times again. Our civilization, for all its achievements, is just one thread woven into a story far older than our species. And to understand the sky is to understand that we live within that larger narrative. The future may include a world where the magnetic poles have shifted significantly from their present locations. Compasses may point in new directions, maps will be redrawn more frequently, satellites will orbit in patterns designed for a different magnetic environment. But none of this changes the fundamental truth. Humanity has always adapted to the planet's slow transformations. What makes our moment unique is awareness. We can see the shift beginning. We can measure it, anticipate it, and prepare for it. Awareness brings responsibility, but also clarity. It reminds us that stability was never guaranteed, that the conditions that make life possible on Earth are part of a dynamic dance between the planet and the cosmos. And in that dance, The magnetic field serves as both shield and storyteller, tracing the hidden rhythms of the deep core and the energy of the sun. The quiet future will not be defined by fear, but by understanding, by a deeper appreciation for the forces that shape our world, by an awareness that the sky above us is not fixed, but a live and evolving boundary between Earth and space. And as the centuries turn, future generations will look back at our time not as the moment when everything changed, but as the moment when we first learned to see the change for what it truly is, a reminder that we live on a restless planet, guided by a shifting shield, moving through cycles far larger than ourselves, a planet that has changed before, a planet that will change again, and a sky that, even in its transformation, continues to hold us beneath its quiet and ancient protection.